begin. Most of the people are here by now. So the last thing we saw in lecture 3 was the derivation and couple of applications of refraction at a spherical surface. So let's quickly go through that again. So we saw that whether you have a concave or convex refracting surface, and in fact, still have some people joining in. Anyway, so whether we have a concave or convex surface, and whether the refraction is happening from denser medium to rarer or rarer to denser, whatever be the case, okay, then an event that a ray of light from a point object somewhere is incident like this, if the center of curvature is, let us say, over here, the point object is, let's say, over here, so this becomes the normal at the point of incidence, then typically the bending of light either towards the normal if it is going into a denser medium, or away from the normal if it's going into a rarer medium, that causes this kind of situation. Here it will typically, let's say, bend towards the normal. So in this case, the refracted ray actually bends further away, so it has to be produced back. So it will give you some kind of virtual image over here, this kind of thing. So anyway, the formula was like this, that if this medium is medium A and this medium is medium B, so this is having refractive index mu A, this is having refractive index mu B, then with our proper sign convention, we have mu B by V minus mu A by U is equal to mu B minus mu A divided by R. So in this, we just have to remember that the quantities V, U and R are with Cartesian sign, and also that the refraction is happening from A, from medium A to medium B. So that is where these come in. Okay. So let's look at a couple of interesting application questions based on this. So now I'm referring directly to a previous year JEE question actually, but came long time back, I think. So let us say what we have here. Is a quarter cylindrical glass solid glass slab. So this is glass. So quarter cylinder of glass. You are looking at the cross section. Okay. And what we have is a ray of light. Oh, sorry, we have so we have a small point source of light. So S. And what we want is that the paraxial rays here should emerge parallel to the principal axis. So So after refraction, this is what should happen. So if this has a radius, let's say r, and this is kept at a distance x. So given r is equal to, let's say, 10 centimeters, and refractive index of glass is 1.5. We have to find x such that the emergent paraxial rays are parallel to the principal axis. Okay. So this is the quarter cylinder of glass. So obviously this point here is the center of curvature. And so obviously this point here becomes like the pole. So your principal axis is this one. The line joining the point object, which in this case is the point source S, with the pole or with the center of curvature. So that one is the principal axis. So just try this out with me. Okay, Samir. Make sure that your sign convention and all the quantities you're substituting are correct. And you also understand that, light is suffering two events. Okay. It is suffering one refraction at a spherical surface, or in this case a cylindrical surface, but for which the formula will be same as the one we wrote above. And then it is suffering refraction again at a plane surface. Okay. And after the second event, what is happening? The rays are emerging parallel to the principal axis. Yes, Uday, I think your answer is correct. So after this thing, it is emerging parallel to the principal axis. That means the final image should be at infinity. Now, whenever the rays emerge parallel to the principal axis, that means the final image that you're getting should be infinity, at infinity. Okay, so continue working on this. I'll just work on the ray diagram. So, okay, so here what we want is that a ray of light which is incident over here. But remember, actually we are dealing with paraxial objects. Okay, so typically this ray is at a very small angle with respect to the principal axis. Now that one should emerge. That one should emerge from here parallel. Now this is a plane surface, so if it emerges parallel, that means here also it is parallel. Its incidence, angle of incidence here is 0. Okay. So that is the key to understand this question. Is this ray only that is emerging out parallel? This is what is happening. So at the second place, there should be normal incidence. Okay. So now you have to just work out the condition for that. Just work out the condition for this ray diagram to fit. But remember, fit with respect to this thing, paraxial rays. I have drawn a non-paraxial ray, but you have to remember that the rays actually that we are talking about are ones for which this angle alpha kind of thing here, this angle is small. So they are paraxial rays. Okay. So you can see that for the first refraction, okay, if this distance was x, for the first refraction, this is the pole and this is the center of curvature. So it is happening air to glass. The object is s. So object distance we should take as minus of x. The image, it should go to infinity because the rays here itself are emerging parallel. Only then after this also they'll remain parallel. Okay, so v should tend to infinity. Okay. And the radius of curvature, the center of curvature is at the point C. So the radius of curvature becomes plus of whatever radius I give you, 10 centimeters. This was 10 centimeters. So now you have to just apply that formula. Okay, mu2 by v minus mu1 by u, that formula. So refractive index of glass divided by v minus refractive index of air divided by u is equal to difference of the refractive indices divided by the radius. Okay. So we should get 1.5 by infinity minus 1 by minus x should be equal to 1.5 minus 1 divided by plus 10. So this will give us 1 by x is equal to 1 by 20, or x should be equal to 20 centimeters. This should be your answer. And you know, once you know this is happening, you don't need to worry about the second event. So here we also understand the second refraction, that one has 0 deviation, okay, or normal incidence, that kind of stuff. All right, people. So hope this is clear. Okay, so let's move on to the next thing. So we'll be seeing some more applications of this. Now before that, I just want to quickly discuss the case of total internal reflection and critical angle. Okay, so this kind of phenomena, as you know, happens when there is refraction, not just at a plane surface, but typically at any kind of surface, from a denser to a rarer medium. For example, if this is, let's say, water, and this is air. Now, suppose typically we are having a situation where we have an incident ray like this. So the refracted ray is like this. So we have that formula in that. If this is angle of incidence, this is angle of refraction. So here what is happening, that refractive index of water into sine I is equal to refractive index of air into sine R. Okay. So R is becoming sine inverse of, let's say, 4/3 times sine I. If we take that kind of typical value. So you can see that R is greater than I. But the other thing you can see is that as your I increases, so does your R increase. Okay, so if I now take a ray which is incident like this, its refraction might happen something like this. So we have a ray like this. Now let's say this angle of incidence here, this is I prime, and this angle of refraction here, it is becoming R prime. So if I is greater than I, or rather I prime is greater than I, implies that R prime also becomes greater than R. So what happens is you go on increasing the angle of incidence. Okay. So at a particular value of angle of incidence, for a certain value of I, what will happen is that your R, which in this case is sine inverse of 4/3 times sine I, will actually become sine inverse of 1, which will become 90 degrees. Okay. So when that happens, so for such case, the angle of incidence is called the critical angle. Okay. And the emergence of light, critical angle, so for I is equal to IC, the angle of refraction becomes 90 degrees, or what we have is what it is called grazing emergence. This is what happens. And the ray of light that is coming out, it is just grazing out the surface. So that is what we mean by the term grazing emergence. Okay, so before we get into this thing, total internal reflection, let's understand what is the meaning of grazing emergence. So a ray of light here will just about graze and come out. Okay. Just about parallel to the surface. This is called a grazing emergence. That kind of stuff. Okay. All right, so that's understood. Okay, now also see that what will happen if the angle of incidence is more than the angle of the critical angle. Okay, so here the angle of incidence was equal to what we call the critical angle, and now we can develop a general formula for this. Okay. So the general formula is like this: is that if this medium is having refractive index mu a, and the medium outside is having refractive index mu b, so obviously critical angle is such that sin r, or you can say mu b sin r, is equal to mu a sin I. Now in this, when I is equal to IC, your R becomes 90 degrees. So your critical angle is given by sine inverse of mu b by mu a, or better stated, it is sine inverse of 1 upon mu of E with respect to B, where we understand that E is the denser medium. So first of all, this is the formula of critical angle in terms of sine inverse. This is something we should remember. And then secondly, what we should remember here, I'll minimize this. Okay. Secondly, we should remember that from A to B, that is denser to rarer, if the critical angle happens to be greater than the the angle of incidence happens to be greater than critical angle, it means that there is going to be no emergence. And instead, there is total internal reflection, as you know. Okay, so that happens in this situation. So at some point of incidence, if our angle of incidence exceeds the critical angle for that pair of medium, then instead of transmission into the other medium, this happens. But for this condition to occur, this angle of incidence has to be greater than sine inverse of 1 upon mu of A with respect to, where this medium is A and this medium is B. In that case, it follows the law of reflection. R is equal to I. It's after all, just like a reflection. So the interface of the rarer medium on the denser medium, it actually acts like a mirror. It creates like a plane mirror kind of situation in this diagram. Okay. So make a quick review of this, and we'll discuss some typical questions based on this also. Yes, that is the idea. Any refractive surface for a rarer medium on the other side can actually behave like a mirror also. Grazing, Sudhir, to answer your question, grazing basically means when something just is, touching a surface. So if when we come to the diagram below, you see for the critical angle case, this emerging ray, it's not coming out into the new medium. It is just basically tangentially touching that surface or grazing that surface. The word grazing means it skids along that surface, that kind of. Yeah, Ninad, to answer your question, refraction through a prism will be the last thing that we'll discuss after we finish about thin lenses. Okay. That is another section of this chapter, so we will discuss about that in detail. But yes, in that also total internal reflection will be an important thing when we discuss refraction through prism. Okay. Now the other thing we want to understand here is from the principle of reversibility of light. We want to understand the concept of grazing incidence. Is also in itself a very interesting concept. Okay. Just a second, I will. Just give me a moment, guys. Yeah, just a moment. Yeah, so let's understand the concept of grazing incidence. So let's say we have an example like this. Let's say this is glass, refractive index equal to 3/2, and this is air. Now we have rays coming from some very distant source, which are actually like this, almost parallel to the surface here. So they are, let's say, incident at a point like this, where the angle of incidence, so they are, this is what is called a grazing incidence. The ray which is incident now, this one, the angle of incidence is tending to 90 degrees. So this is what is called grazing incidence. And what will happen for the refracted ray here? It will refract in at an angle of refraction which will be equal to the critical angle. So that will be given by that formula. Sine inverse 1 upon refractive index of glass with respect to air, denser medium with respect to. So this will be sine inverse of 2/3. So for grazing incidence at the interface like this, the ray will actually bend into the denser medium, but the angle of refraction will be equal to the critical angle for that particular ray. Okay. So this is another concept related to PIR and and critical angle, which is called the grazing incidence case. So this is another something that we should be mindful of. Okay, now this kind of situation can happen for something like this also. It can happen for a spherical surface also. For example, we have a glass sphere. Here also we can have the condition for total internal reflection. So if we have an incident ray inside this, it can well happen that this emerges like this, as if this can happen. But for that to happen, what will be required is that your angle of incidence, in this case, will be this angle. Here now, this angle will have to be the critical angle, so that this angle becomes 90. So this is again that kind of case. This medium is mu A. This medium is mu A. Okay. So let's see a question based on this. So here this is what happens. A ray of light is incident on a glass sphere tangentially at the point E. Now refractive index of glass is, let us say for this one, it is 5/3 or approximately 1.67. Instead of 3/2, which is 1.5, it is say 5/3. So first of all, trace the path of the beam as it refracts into glass. Locate the point of emergence from the glass and find the net angular deviation So what we mean by angular deviation is if we have some kind of a system and there is an incident beam like this and it finally emerges like this. So this is the emergent beam. This is the incident beam. Then the total angular deviation that it suffers is this. This is the angular deviation, delta. Okay, so that net angular deviation, delta net you have to calculate. So I'm just minimizing this and just try out this question. You'll understand very easily. This is the application of the grazing incidence and angle of critical angle concept over here that we'll be applying. So we will just try out this question. You can get the answer in terms of the radius only, but or you can take some arbitrary radius, let's say 50 centimeters. So you can correct. Ganesh correct. Yes, Bhumik correct. So what happens here is so if we assume some tangential kind of incidence over here at this point E. So we'll drop a normal at that point E, which in this case will be nothing but this radial line at the point E. Let's say so our angle of refraction being 90 degrees, we can see that this will refract in something like this. Okay. So this angle here will be equal to the critical angle. Okay. So actually the refraction will not look like this. The refraction will look more like something like this. I'll show you why just in a moment. So this is going to be the critical angle. So this critical angle is going to be sine inverse 1 upon refractive index of glass with respect to n. So it's going to be sine inverse 1 upon 5 by 3. So sine inverse 3 by 5. So it's 37 degrees. So the other thing you can see here is that the angular deviation this has suffered right now, we can call this as a delta 1. The first refraction so is creating first refraction air to glass. This is occurring with that situation, okay, what we call grazing incidence. So I is equal to 90 degrees. So R is equal to critical angle, which is so as a result of this, you can see that the deviation that is happening here, delta 1 is 53 degrees and it is clockwise. So keep that in mind. Okay. Now let's see the second event. Now the second event is happening over here. So if we now draw another normal, at this point like this, and also just to help us out. Anyway, so if all this were drawn to scale properly, realize that for the second incidence, my angle of incidence is again becoming equal to critical angle. So this I will be equal to this. That you understand from the symmetry over here. This whole angle gets bisected and all that. So this is again going to be for the second refraction from glass to air. I is equal to 37 degrees, which is equal to critical angle. So this time R will be 90 degrees, which will mean that there is a grazing emergence. So here it means that this will come out like this. This way. So this incident ray will now come out as this emergent ray, which is actually along this tangent. This will be 90 degrees. Like this. Okay. Now, more importantly, here you'll be able to see that this deviation is my second deviation, and this deviation is also going to be another 53 degrees. Okay, so delta 2 is again 53 degrees. So my net deviation will actually become the sum of these two. So if you produce this one forward and this one back, so you see that overall in your path, the deviation that is happening is this. So in this case, we will express the deviation as (106 degrees in my diagram clockwise. So this is sort of, yes, and then we can find the distance of this point. Let's say it emerges at the point B. So B is just the chord length. So the chord length we can find as 2r cos. So that chord EB has a length so 80 centimeters. So it will emerge from a point 80 centimeters away from the point of incidence. Okay, so you have these type of interesting, slightly abstract type of applications also for spherical surfaces, not just the paraxial rays, but whenever there are paraxial rays involved from a point source kind of thing, you have to use that UV formula. Otherwise, you have to stick to the basics. And just like we discussed on spherical mirrors also. If your ray incident is shown, which is non-paraxial, then you have to use the fundamental, which is the laws of reflection. So similarly here, if your rays incident are not paraxial in that sense, then you have to use the fundamental principles, which is Snell's law. What we've used over here is an application of Snell's law for the case of grazing incidents, and then later grazing emergence. Okay, people, so hope this is clear. Now we'll see another very interesting application of this concept. So next example. So we have a perfect hemisphere of glass. So we have a solid glass hemisphere. This is made of special high density ground glass. So it has, the glass has refractive index of 2, okay, and the radius, let's say 20 centimeters over here, okay. Okay, now we have so these two lines are at 45 degrees. Okay. Now we have incidence which is like this. This is okay. So we have incidence which is like this. We have a narrow beam of light. It's coming from infinity like this. So we have a narrow parallel beam, like a laser beam, it's very focused and narrow from infinity. Okay. Find the position and type of image form. Okay. So this is our next example. Just try this out, people. Just try this out. I'm just written. So start by solving what's happening in the first refraction here. The first refraction is happening at a spherical surface going from, yes, very good. Ganesh, you have got the concept of the question correct and the answer also. So the first refraction is happening at this surface over here, which is a spherical surface, okay, for which the center of curvature is here. The incident rays are coming from infinity. So, and they are paraxial rays, because you will take this as a principal axis. So the rays are very close to the principal axis. It's a narrow beam. So if you were to just do this in terms of events, so the first event here is refraction from air to glass at a convex surface. For that first refraction, we don't need to worry about the second event that is happening. We just need to keep in mind that, so what is ahead doesn't matter over here. What matters is that the center of curvature of the mirror being here, of the spherical surface being here, and this being like the principal axis. So what is here actually doesn't matter. This whole thing could be glass or whatever, it doesn't really matter. So any ray of light like this, what will happen to it after refraction? So let's try to understand this. Okay. So the refraction is happening from air to glass. Okay. This point is the pole for my system now. And let us take this side as positive and take this side as negative. So my radius of curvature, but with proper sign, I will write as minus of whatever that was. How much I taken? 10 centimeters or 20 centimeters. So minus of PC or minus 20 centimeters. Okay. And U I'll take it infinity because the incident ray is parallel to the principal axis. So mu B, that is refractive index of glass upon B, minus mu A, that is refractive index of air upon U, is equal to the difference divided by R with the proper sign and everything. So to find the position of the image, you have to see that 2 in this case because I've taken refractive index as 2. Minus. So we'll see that V comes out to be minus 40 centimeters. What does this tell us about the first image? It tells us about the first image. This will deviate ever so slightly such that when meet the principal axis image. This is the position of the first image. I1. So similarly, we had another ray here. So you have all the rays in between these two, which is the beam of light. So this would also, after refraction, where now this distance from pole to here, this would become 40 centimeters. It's minus 40, so this is the meaning of this. Okay. So this would happen if there was glass all over here. But remember, this is a hemisphere, so the glass is finished somewhere here. Okay, so we have to go back to the original diagram now and understand what's happening for our given system where there is more than one event happening. So for our given system here, what's going to happen is very interesting. but actually we want to continue this line a little bit more. Okay, so now I'm going to, just for the sake of diagram, draw the rays which look a little bit non-paraxial, but you imagine that they are more or less paraxial. Or let's see, you might be able to manage drawing something which looks more or less paraxial. So this ray of light would, after suffering refraction, go on a path like this, such that it should meet the principal axis somewhere. Similarly, this ray of light would, after refraction, go on a path like this, that it tends to meet this. So this point would have been my I1. So what is happening here is this. This is my first event. This is done. But now this image is not formed because these rays are now incident over here at this plane surface. Okay. So that's why this actually becomes like an image which is behind the next event. So I1 becomes like a virtual object for the second event. So first event we've already solved. Now let's come to the second event. So second event is, it is incidence at the plane surface between glass and air. And for that, the object is in fact I1, which is a virtual object. That whole concept of virtual. So I mean, just from the perspective of this second event, what is happening is this: what is happening. This is your interface. You have air, glass, but your incident rays are not coming from a real object in front. Your incident rays are like this. They intersect at a virtual point behind. I mean, these are the incident rays. So your incident rays are intersecting at a point which is actually like this. This is a virtual object. So this is what is happening. So that is what we mean by the concept of virtual object. So that concept only here is happening over here. These rays, they are incident in such a way that they are not coming from some real point in front of this surface. They are going behind. And you can see that for this incidence, okay, which is a normal, this one is a normal. So for that incidence, the angle of incidence is more or less this one, which is 45 degrees. Okay. So the angle of incidence is give or take a little bit less than or more. Okay. So the angle of incidence is just about 45 degrees, slightly more or slightly less. We can say it is basically 45 plus minus some delta. The delta is a very small angle. It is slightly deviant from this. Okay, so now the interesting thing is you can see that if you want to go by formula, you would have to apply Snell's law, but that would give you an absurd result. If you apply Snell's law, you will get the angle of refraction is not possible. Okay? If you apply Snell's law, which will actually tell you that there's PIR happening. Okay? That mu of glass into sin I is equal to mu of air into sin R. So if you substitute this, you will get 2 sin 45 degrees is approximately equal to the value of sin R. So you will get sin R greater than 1. Greater than 1. So that's not possible, as you can see. So the moment that thing happens, you realize that okay, now refraction is not happening. So what is the possibility that is happening? There is TIR. So you understand there. Therefore, no refraction. Instead, there is totally internal reflection happening, because you can see the critical angle for this pair of media is sine inverse of 1 upon refractive index of glass with respect to air. So that in this case is sine inverse of half. So that is 30 degrees. So no wonder there is TIR happening, and we didn't get an answer for Snell's law, because critical angle is only 30 degrees, whereas for the second case, the angle of incidence was nearly 45 degrees. So I is greater than critical angle. So what that means is now there will be TIR, and the plane surface acts like a mirror. This is what happens. That plane surface over there, it in fact acts like a mirror. So यहाँ पे this incidence is happening such that now this surface is acting like a mirror. So the moment it acts like a mirror, these will reflect back, and they'll produce. And now we'll come to the concept. We'll come back to the concept of virtual object for a plane mirror. And understand that virtual object gives a real image, such that the real image is in front of the mirror at the same perpendicular distance as the virtual object is behind the mirror. We'll use that concept now to understand the second event. So the second event is converted from a refraction to effectively a reflection at a plane surface. So now if you just follow the ray diagram path for the reflected rays, you will see that there's no third event that happens actually. You'll understand why that happens. Just follow the ray diagram. But for example, in the same question, if I had taken the refractive index of glass different, instead of 2, I had taken like the previous question 5/3. So the critical angle would have been 5/3 में ज़्यादा हो जाता. Suppose I had taken 5/4, like 1.25. So the critical angle would have been 53 degrees. So here the angle of incidence would be less than the critical angle. So then what would happen? The rays would simply pass through that second surface, go by refraction. So for that, then we have to use the real depth apparent depth formula, but with virtual object. So that is also a very interesting thing you can try out. Okay, so now I'm just going to try see if I can get away with. So that will save us a lot of time. So now I have a situation like this where I can see that this TIR will result in this kind of thing. This ray deviate and go like this. This ray go like this. Okay. So this one is coming. So let's say if this was ray 1, this is ray 1, this is the reflected version of ray 1. If this was ray 2, this is the transmitted version, and then this is the TIR version. So ray 1 and 2 and all the rays in between them will finally, now we will understand why this will be here, because if you just draw a guideline kind of thing here, understand that this was lying on like the virtual spherical surface because it was exactly 40 centimeters. So that is very critical to the values in the question. Now, because the refractive index is 2, that is why this was coming as 40, this whole thing. So this was 20 behind. So now this will also have to be 20, because the idea of the reflection will be actually this, that the final image will be in front of the mirror at the same distance as the virtual object is behind the mirror. Okay. So this will have to be the thing for it. So this I1, which is a virtual object, will now give I2, which is a virtual image. And that virtual image happens to be just on the surface of the mirror. So these rays will not suffer further deviation as they come out. Okay, so basically, like a parallel beam of light will give you a spot of light which you actually see over here. So the final image is actually a real image, because there's actual emergence of light rays over there. It's not a virtual. I1 is a virtual point, but I2 is real. Okay. So this event, virtual object, gives you a real image. So the concept that we are using over here is something we've seen before, the concept of virtual object and real image. So if you have a plane mirror like this, and the rays of light which are incident are like this, and after reflection what happens is this. So incident ray is giving you a virtual object behind. The reflected rays give you a real image, such that this distance becomes equal to this distance. So this concept is now being applied over here. And then just using geometry and all, you can find out that where exactly I2 is located, because this angle will be nearly 45 in this diagram. So again, just guideline like this. This angle will be nearly 45 degrees. So that is the final position. So this I2 becomes the final image, which is incidentally a real image. It's a real. So if this is like a narrow beam of laser light, you will see a red colored spot at that point. In these kind of high precision optical experiments, typically laser light is used for demonstrations because it's highly directional and does not get diffracted by dust particles in air and all that. So it's the experiments are more precise. We're able to achieve that paraxial condition also better. Okay, so geometrical optics always has these kind of questions which are a little bit abstract and which you cannot solve by just application of the standard formula every time. You have to be aware of the fundamentals and also aware of all the variation in the fundamentals. Like TIR is a variation of refraction. Okay, it happens. Now TIR is something very easy to understand when it happens, because if you even by mistake think that there is refraction happening and apply Snell's law, it will tell you that okay, Snell's law is giving you a wrong result. That means there must be TIR happening. Like we did experimentally here, we saw that the angle of refraction, assuming refraction, was coming such that sin r is greater than 1. So the moment that happens, you realize that okay, there's something else that is happening instead of refraction. So now, as a self exercise later, I would also ask you to work out this question with a different value of refractive index. Keep everything else the same. Take the refractive index of glass as 5/4 or 1.25 and repeat the problem. And you will get an interesting geometrical situation over here. Again, you will be solving only two events, but the second event here will not be a TIR, it will be a refraction. And for that, you will have to apply Snell's law and apply some kind of geometry to find where the position of the final image is. Okay, people. So hope this is clear. Okay. So as I said, there are virtually unlimited number of problems of these type, which are very interesting geometrical problems where you have to keep applying the fundamentals or the UV formula or whatever, whichever is applicable. But now moving on to the next major application of this formula, refraction at spherical surface, which is what happens in the case of a thin lens, because there are two spherical surfaces which are very close to each other. Okay, so let's first of all understand thin lenses as the next thing. So a thin lens by definition, it's a refractive optical medium bounded by typically two spherical surfaces such that the thickness is very small compared to the radii of curvature. That is the definition of a thin lens. Whereas a lens is just any optical medium bounded by two spherical surfaces. So typically, if I have this kind of situation, so I have this and in the interest of keeping the geometry quite perfect. Okay. No, what will happen is the moment we have to take a thick lens into account, we will have to solve that problem by fundamentals, by using the this formula, that mu v upon v minus mu a upon u twice. Okay, so this is an example of, whereas the shortcut formula, which is what we call the lens maker's formula, the focal length formula that we use, okay, that will be applicable only. So this is surface 1. So this has a center of curvature here. This has a center of curvature here. This is surface 2. So this is becoming, now this thickness is suppose W. W should be very small compared to the two radii of the two surfaces. Okay. So this is an example of what we call a biconvex thin lens. Okay. This is glass, for example. Similarly, we could have a situation like this, where these two surfaces are part of these two spheres. So this one has a center of curvature here, this one has a center of curvature here. So this is an example of a biconcave thin lens. Again, thin lens because here this thickness, the pole to pole thickness, this surface has a pole P1 here, this has a pole, so this width is very, very small compared to R1 and R2. So these are the two basic type of lenses, and then obviously there are all combinations of this that you are aware of from the beginning. You have plano-convex, plano-concave, and you also have concavo-convex. These are the different types of lenses. But in all of these, we are always applying the condition for thin lenses that this pole to pole width has to be very small compared to the individual radii of curvature of each surface. So this is that definition and geometry of the different types of lenses. Okay, so next up we will see lens maker's formula. For these thin lenses. So remember, this is applicable only for thin lenses. If you have a thick lens, then we have to actually go back to fundamentals and adjust to find the required condition. Okay. So lens maker's formula is basically a formula that is used by people who, the opticians who make the lenses. They want to create a lens of a particular focal length. So how they will, what combination of radii of curvature they will use, depending on what material they are using, which is having a particular refractive index. Okay. So let's take an example of a biconvex surface or biconvex lens, but we will see that the final formula that we get with Cartesian sign convention applied, it is uniform for all types. I mean, it's a universal formula for all types of. Okay, so this is a biconvex lens, thin lens. Okay, let's take this as surface 1, and this one as surface 2. So surface 1's pole is here and center of curvature is somewhere here. Because surface 1 you can see is this one. So it's like this. And surface 2 center of curvature is over here. Okay. So in this case, we will call the line joining the two center of curvatures as our principal axis. Now to understand that if, for example, I have kept, so this is center of curvature 1, center of curvature 2. This is a glass lens, let's say. So refractive index of glass is mu g, and this side and this side both there is air. So we'll take refractive index as the generic term mu, though we know it's 1. Now imagine that I have a point object somewhere over here. Okay. And I have to find the position of the image due to the paraxial rays. So again, we will first solve this by using the generic method of series of events. Refraction from air to glass. So if this is the incidence, here you can see that for this surface the normal is somewhere here. Okay, so assuming this would bend towards the normal, so we are going to get a slight bit of deviation here like this towards the normal. Such that if you were to produce this back, it would go back further. It would go back somewhere here. And then the second one, the normal is becoming this line. So this time it would bend away from the normal. So let's assume it bends enough away from the normal to actually make this a convergent thing. It need not be, but let's just assume it's becoming convergent. So this would become the position of the final image. And this final image, as you can see, is a real image because it is coming from actual intersection of this. So how do I find the relation between? So I'll take the pole as common because the width is negligible. So the relation between OP, PI and these two, C1P and C2P. How do I get that relationship? Let's understand. Okay. So for this, what we'll do is we'll solve the refractions back to back. So the first event, as you can see in the diagram above, if you just recall, it is refraction from air to glass. Okay, so the formula is refractive index of air divided by V minus refractive index of glass divided by U is equal to this difference divided by R. This is the formula. Okay, now for that, the object is which one? O. So the object distance we will take with the sign convention will be minus of OP. Okay. The center is C1, which if you remember was on the positive side. So we'll take R as plus of C1P. And the image, let's say I1, which I don't know. So the image distance we'll take as V1, which is unknown. Okay. So I'm just relating this with the diagram above so that you have clarity. Okay. So according to the diagram above, what I'm kind of hinting at is that this is what should happen. That when the light from this point object over here is incident over here, for which the normal is something like this, let's say. So it bends towards the normal, a little bit like this, let's say. And you produce this back, it should give you your I1 over here. This is assuming that this is what will happen. It will not bend enough to actually converge. So assuming that over here. So now apply the formula to this one. So mu2 by V or mu B by V. So that is refractive index of air, but divided by V1 minus refractive index of glass divided by minus of OP is equal to mu A minus mu G divided by plus of C1. Now what we'll also do is we will take this as R1 with the sign, and we will take this as our original object only. Okay, so this gets converted to this formula. Oh, sorry, this should be glass minus air. Air to glass now. This correction is air to glass. So this is actually in reverse. The second refraction, which is happening from glass to air, that will have these. So refractive index of glass by V minus refractive index of air by U would be glass minus air divided by R. Okay, so this formula we can convert to this, that refractive index of glass by V1 minus refractive index of air by U is equal to glass minus air divided by R1, where R1 will be substituted with the proper sign minus, sorry, in this case plus of Cp. Okay, so this is what we are getting in the generic form. It should be applicable for all kinds of situations from the first refraction. Okay. So that's done. Okay. Now let's understand what is happening to these rays. These rays don't actually continue this way. They are now incident on the second surface. You know? So these rays over here, they are incident on the second surface. So second event here this one is happening from glass to air, and for this the object is actually I1. So in my diagram it's a virtual object. Okay. The image is, let us say, I2, which we want to find out, but this will become our final image. Okay. And the radius will in my diagram be minus of PC2, but in general we'll write this radius as R2 with the proper sign depending on whatever kind of surface it is. Okay. So it will become mu2, that is refractive index of air divided by V, which is V2, let's say, minus mu1, which is refractive index of glass divided by V1. So because of this, we will have to take the object distance or object position as V1, and whatever sign the object position has in the first diagram, that sign will be carried over here. So it takes care of itself. Okay. So in the first diagram, in the first refraction, if I'm getting, if I'm getting V1 as negative, so I'll put V1 with the negative sign over here. V1 with its sign will be put over here. Whatever V1 we are getting by solving this equation. By solving this equation, whatever V1 we are getting, if it is negative, then the object becomes a real object for it. If it is positive, then the object becomes a virtual object. Okay? So this is from equation 1 above. Okay? And sign convention takes care of it. If V1 is negative, that means it becomes a real object for the second event. Okay? If V1 is positive, it becomes a virtual object. So that is the advantage of sign convention. It takes care of what is required. So this is refractive index of air minus refractive index of glass divided by R2. Again, R2 will be substituted with a proper sign. So for my biconvex lens, the proper sign would be minus of that distance, PC2. Okay. So this is my second. Now in this, what is happening is that your V2 is only V, that is the position of the final image, which is nothing but I2 with respect to the pole. Okay. So the diagram that is catering to this now is actually this one. we have this surface whose center is somewhere here. Pole is this. Okay. And on this we had the incident rays, which are actually like this. These were the incident rays. They're appearing to come from some I2 which was over here, but actually some I1 which was over here. Actually the object was here because before this something else happened, but they appear to come from here. Okay. So now we are saying that okay, after refraction, suppose this is happening. So they are going and meeting the principal axis somewhere here. So this is my I2, which is the final image. Okay, so that's the second part, visualized as a diagram. Okay, but we have already written the formula for it. So now what we have to do is we have to solve equation 1 and 2 such that we get the relation between u and v. Okay, so for that you just add equation 1 plus 2. So the moment you add the two equations, you will see on the left hand side, it's very simple. You have refractive index of glass divided by V1 minus refractive index of air divided by U. Plus from the second equation, we have refractive index of air divided by V2, which is basically V. So this V2 will substitute as V minus refractive index of glass divided by V1 is equal to, now on the other side, you see, we had mu g minus mu a divided by R1 in the first equation. And the second equation, when we added, just had negative of this, mu a minus mu g divided by R2. Yeah, but I'll just explain the steps in between also. So don't worry. So this and this term cancels. So we have refractive index of air into 1 by V minus 1 by U. Is on the other side, if you take refractive index of glass minus refractive index of air common, 1 by R1 minus 1 by R. So I've got the relation between V and U, and that relation is now becoming this. That relationship is 1 by V minus 1 by U is equal to, if you just divide this on this side, so it becomes refractive index of glass with respect to air minus 1. Or anyway, mu a is 1, but if you had some other medium, like some liquid, like water, so this would have become refractive index of glass divided by water minus 1. Okay, so this is glass with respect to that medium into 1 by R1 minus 1 by R2, where remember in this formula, U has to be substituted with the proper sign. So in my particular example, with the proper sign, it is actually minus of OP, whereas R1 and R2 are also to be substituted with the proper sign. So referring back to for the above diagram, okay, U is minus of OP, R1 would be positive because it was on that side of PC1, whereas R2 would be minus of PC2. So I'll minimize and show you the whole thing. So don't worry. Okay. But this becomes the generic formula. So this formula is actually applicable for all the cases. This is the general formula. So it will work for all cases. Biconvex, biconcave, okay, concavo-convex, everything works for, as long as we substitute with the proper sign convention. Okay. So I'll just take you through the steps of the derivation once more. Okay. So it is nothing but two refractions which are happening back to back. So in this diagram, you can see the first refraction is happening from air to glass, where the object is actually O, and the image is this refracted ray inside glass. If you produce it back, it meets at somewhere like this I1 over here. So this is the first refraction. So the first refraction is from air to glass. So it is refractive index of glass by V minus air by U is glass minus air divided by radius. And that radius, we are now seeing the radius of curvature of this first surface. So the general value we are writing out for it is R1. But in this particular example, the value of R1 would be plus of C1. Okay. And that is giving you an image of V1. So according to what my diagram looks like, V1 should come out as something negative. But in another case, it can come out as positive also. It doesn't matter. Okay. So the general formula between V1 and U, and of course R1, is this formula. This is what would happen if there was only one event happening over here. Your final position of the image would be V1. Now what is happening is that these refracted rays which are over here, they are actually incident on the second surface, which is the interface between glass and air. So after this event is over, the second event which is happening in series is this one. Refraction from glass to air, for which the incident rays are these transmitted rays inside glass. So that means the transmitted rays inside glass, this transmitted ray, this is acting like the incident ray. So this is coming from from I1. No? It's coming from I1. So what is the object for this second event? It is I1. And what is the image? Let's say it's some I2, and that is nothing but the final image. So that's how I have solved the second case now. Refraction from glass to air with the object as I1 and the image as I2. So refractive index of glass divided by of air divided by V minus glass divided by U is equal to air minus glass divided by radius, which is R2. So again, referring to the diagram above, you can see R2 would be minus of PC, but actually R2 could be anything depending on which case of lens you have. Okay. So let's take it step by step. You can first understand the first event here. Right? Come to this formula, then I'll take you below to the second formula. And then combining the two formula, you'll see you get the relation between the original object O and the final image, which is I2, which in the above diagram is labeled as I. This one is only I2. The image after the second event. Uday, I'm sorry that you had a disconnection, but you will be getting the full video of this, so don't worry. Video and the whiteboard notes, both of them I'll send you. So. Okay, so that's your first event. Now this image I1 from the first event is becoming the object for the second one. So that is where this is. And then in the last step, as you can see, we've just combined equation 1 and 2. And by that combination, after cancelling of the common things and all, we'll get the final formula. And that final formula is, it's not exactly lens maker's formula, because lens maker's formula is about focal length. But from that only, next step, we'll get lens maker's formula. By putting U as infinity, the position of the final image V will become the effective focal length of the combination of events. Okay, so the combination of events is basically the events because of a lens. So that will become the focal length of the lens. Okay, people. So just scrolling down to this now, so you can see that this is the result that we are getting between UV and the radii. Okay. Now to find the focal length for the lens, all we have to do is now imagine that the incident rays are parallel to the principal axis and figure out where the position of the image will be. That is the concept of focal length. So in this formula, so to convert this into lens maker's formula now, what we have to do is make U tending to infinity. So the position of the image becomes the focal length. So as you can see, that gives us the formula of focal length of the lens. So we get this relation that 1 upon focal length is the refractive index of whatever glass we've used with respect to air minus 1. Now there's a reason why I'm writing it like this, because we could write this as absolute also. But this is to emphasize that this is the refractive index, sorry, this is the focal length of the lens when we are using it in air. When we use it under water or something, this A will be replaced with the water. Okay, so we remember R1 and R2 must be substituted with the proper algebraic sign, Cartesian sign. Okay. So this particular formula is now called the lens maker's. If you want to be very technically correct, it is apostrophe on plural. It's a formula used by lens makers. So the apostrophe comes after S. Not significant at all. Final point. Okay, so I just told you it's used because the opticians or lens makers use this formula to actually craft the lenses or machine the lenses. The way they fabricate it, the choice of radius of curvature so that they get the required focal length. That calculation is done from this formula. Okay. Now let us see the actual working with some examples. Now let's start with a biconvex lens like this. Where the refractive index of glass is, let us say, the standard value 3/2. Now this surface has a radius of, let us say, 90 centimeters. And this surface, you can see slightly more bulging. This surface, the way I've drawn it. I've tried to draw it like this, that this surface is more bulging compared to this surface. So more bulging means that the smaller radius. Let's say this surface has a radius of 60 centimeters. So let's find the focal length. Okay. First of all. So now I'll show you something interesting, that your focal length is symmetrical. It doesn't matter whether light is coming from this side or from the other side, it will be the same. Let's understand that thing. Okay. So this side, center of curvature. So now let's imagine that we are talking about, in the first case, parallel beam of light coming from infinity paraxially, but from this side. So whatever is the position of the image, that will become our focal length. And let us go with our normal sign convention that this side is negative, this side is positive. Let's say the thickness of the lens was a few millimeters, so this is very small compared to the radii. So see here, our language will be like this, that light is hitting this surface first. So this will be taken as surface 1. Okay. And this will be our center of curvature C1. Whereas light is after that hitting the second surface. Okay. So the second center of curvature will be the center of curvature of this surface, which is like this. So it's C2 again. Where we know that PC1 was 90 centimeters, PC2 approximately, of course, because there is a thickness involved, but so that is 60 centimeters. Okay. So now when we are using, so just minimizing this to show this in context of the information I gave you. So welcome back, Vedant. It's unfortunate that some people are having internet connectivity issues today. So this is one of the unfortunate things about the online lectures. But then the fortunate thing that we have to overcome this is that we have the video lecture which will be available later today. So you can just repeat that section. Okay. So yeah, so I'm using this data, but I'm using this data in context of this ray diagram now. That the ray of light coming from infinity is coming from the left. So it is hitting the 90 centimeter surface first. So that surface is center of curvature label as C1, and in the centimeter surface next. So that one I label as C2. Okay, so this is very important. It's in context of where light is coming from. It's not that every time the left surface must be taken as R1 and the right surface must be taken as R2. It depends on where the light is coming from. Okay, so that's important. So with proper sign convention now, you'll see that we'll have to take R1 as plus of 90. And we'll have to take R2 as minus of 60 centimeters. This choice of sign convention in R1 and R2 is relevant with this diagram. Okay, so where the object is very important when we take R1 and R2. Okay, so with that now I will say that okay, the focal length 1 by F should be equal to refractive index of glass with respect to air minus 1 into 1 by R1 minus 1 by R2. So now let us substitute with the proper sign convention. So this is becoming 3 by 2 or 1.5 minus 1 into 1 by R1 with proper sign was plus 90 minus 1 by R2 with proper sign R2 is minus 60. Okay. So next you take LCM and all that and you see. So 2 plus. So it's becoming how much? 360 by 5, or the focal length is becoming 72 centimeters. But more importantly, it's positive. So the focal length is positive of 72 centimeters. We'll go back to the diagram and understand what that means. So that means that the focal position will be somewhere. Because remember, this is 90 centimeters. So this means that the rays, when they emerge from here, whatever is happening in between is fine. When they emerge from here, so whatever happens inside here is not what we are looking into in the formula. But this will be the case. Okay. So this is what the formula is telling us, the direct application of the formula. Now we can also solve this event by event. Okay, that would also be an interesting way of verifying this, but if you do that, you will get this. So what finally this is telling you, that this is a converging lens. So it's making light converge of focal length. Okay, when we just use the general term focal length, there's no sign convention involved. 72 centimeters. So that means parallel beam of light incident on this will actually converge to a real point behind. Okay. So a real point behind, which is called the focal position, which is 72 centimeters behind the common pole. So that is the final interpretation of this. Okay. What I will also show you is that if I took the parallel beam of light incident from the other side, it would give the same result. I'll get my focal length with sign convention as minus 72, but the result will be the same, that it is ultimately a converging lens. It is ultimately a converging lens of focal length that much. That is the conclusion that I'll get. And the interesting thing is that even though the radii are going to be in reverse order, it's going to first encounter the 60 centimeter convex surface, then the 90 centimeter concave surface for it this time, but it will be same. The focal length on this side will be symmetric. It will be 72 centimeters to the left of the pole. So that's another important aspect of lens we have to understand, that though the lens is, the two sides are having different amount of curvature, but the behavior of the lens is consistent or symmetric, irrespective of which side light is coming from. So another way of expressing that is, if I were to flip the lens, it makes no difference at all. Whether it is 60 and 90 or 90 and 60, it makes no difference at all. This is true for all lenses in all situations. If the radii are equal, then you can see it will become 1 by 90 minus of 1 by minus 90. So now let us take that case where light is incident from the other side. So if you were to have this situation, okay, then what would happen now is that this would become our first surface. But I'd have to label its center of curvature, which is somewhere here, as C1. And this would become the second surface that light is hitting. Okay. And that center of curvature is C1. And we know that PC2 is distance-wise 90 centimeters, whereas PC1 is distance-wise 60 centimeters. Okay, because this had 90 centimeter radius, this had 60. Sorry, this had 60 centimeter radius. This had. Okay. And we don't even need to reverse the sign convention. We can keep this side positive and this side negative. There's no problem with that. Okay. So we will get 1 upon F as refractive index of glass with respect to air minus 1. 1 by R1 minus 1 by R. But the only thing is now I'll have to substitute R1 as minus PC1. So that is minus 60. And I have to substitute R2 as positive of PC2. That's positive of 90. So you will get the same focal length but with a negative sign because it's now on this side. So we have 1 by minus of 1 by plus 9. So solving this further, we get the focal length as minus 72 centimeters. So this doesn't mean that it suddenly changes behavior as a lens. It's still acting like a converging lens. So this tells that it is a converging lens. So this is one important aspect to understand about thin lenses, that they are symmetrical from either side, or if we flip the lens, their behavior does not change. Now, later when you're revising today's lecture, what I would like you guys to do is also get this distance focal length by using the fundamentals. That is two events, refraction from air to glass. So for that, the U is infinity because the beam incident is parallel to the principal axis, and get the position of the first image I1. Then whatever that first image is, whether it is behind the second surface or in front of the second surface, so it will act like either a virtual object or a real object for the second surface. But the second surface is creating refraction from glass to air. And finally, in air, whatever second image that you get, that is your final image. So its position should become the focal length. So if you're taking, for example, this diagram, you should get the position of the second image at 72 centimeters to the left of the the second surface. So that will also give you confidence in your application of sign convention, and also the idea that you can verify the result you are getting from the direct lens maker's formula is the correct one with respect to the this thing, the fundamental application. But then you'll also learn that if the width was significant, how you would incorporate that. You would have to adjust the U2 for the second for the second refraction according to the width and the thickness, because you cannot take the common pole. Then you'll have to take the pole for the first surface separately, the pole of the second surface separately, and you'll have to adjust UV. Yeah, so if the radii are same, so to answer your question, that is the situation which we call symmetric, let's say biconvex, or we'll come to biconcave also next. Okay. So symmetric biconvex lens may, suppose we have this situation. This also has a radius of 90 centimeters. This also has a radius of 90 centimeters. But in the case where light is coming like this, we'll be substituting R1 as plus 90, because the first surface is this one, its center of curvature is here. The second surface is here, R2 as minus 90, okay, in the formula. So when we do that, you will see something very interesting. If your refractive index of glass with respect to air happens to be 3/2, your focal length will come out to be 90, okay, but with proper sign. This doesn't become infinity, okay, because there's the sign of this also. So when you solve this, you get the very interesting result that the focal length comes out to be 90 centimeters. But that happens only when the refractive index of the glass is 3/2, because this term has to be half. If it was something else like 5/3 or 5/4, then you would not get the value as the same. So it's like a coincidence in this case when the refractive index is 3/2. Okay. Now the case where it can become infinity, that thing is different. That is a case like this. When you have a spherical surface of glass, a thin spherical surface. So then both the center of curvatures are at the same place. C1 and C2 are at the same place. So that is when your 1/R1 minus 1/R2 will cancel out. So here the focal length will become like a 1/0. Focal length will tend to infinity because 1/f will be 0. And that you understand why it happens. Because here the emergent ray just comes out parallel to the incident ray. It's a bit of lateral deviation. But then typically we don't treat this like a lens. It's like a thin spherical surface. Okay, so let's see. Incidentally, in this now, another thing you can be asked is the same question above. Find the focal length of the above lens underwater, okay, where the refractive index of water is, let us say, 4/3 or approximately 1.3. So let's understand this. Okay. I'm just refreshing the screen because I'm getting a lag, but just try out this. So the same lens as we have taken above, I want you to find the focal length of that thing which we will get. So I wanted to find the focal length of that lens if we were to do an experiment, an optical experiment with it underwater. So the medium on both sides of the thin lens is water, which has a refractive index 4/3. So this situation now, same lens is under water. So you don't need to do any fundamental calculation. You can just understand it this way, that the focal length in water is refractive index of glass with respect to water -1 into 1/r1 minus 1/r. Now compare this with the normal situation, that is the focal length in air. That was refractive index of glass with respect to air -1 into 1/r1 minus 1/r. So next what you do is you just divide these two equations. So your R1, R2 term all gets cancelled out and you get a very convenient result. So equation you want to find in water, so let's say 2 divided by 1. So you get focal length in water divided by focal length in air. So that is becoming this divided by this. So this is 3/2 minus 1 divided by, this will become 3/2 divided by 4/3. So this is a very convenient way of doing this calculation. So focal length in water divided by, this was 72 centimeters, is half divided by, 9/8 minus 1. Okay. That's 1/8. That's 4. So you can see the focal length is significantly increasing. It's becoming 4 times. Why? Because the bending of light is happening with less deviation now. Now, दोनों के बीच जो refractive index का variation है, that is less. Now, in one case it was 1 and 3/2. Now it is 4/3 and 3/2. So less variation in refractive index means less deviation of light. Less deviation of light means that the rays don't bend as convergently. The amount of convergence is less. So the focal length has to move fast. So 288 centimeters, 4 times this, the focal length will become. So it's less effective in bending light. The amount of bending is becoming less sharp, or the deviation is becoming less. Okay, so through the above question, we've also understood why a biconvex lens, whether or not it is symmetrical, it doesn't matter. But as long as it is biconvex, so both the sides are having convex surface, it will always act like a converging lens. It will always give you a real focal point. Parallel rays from infinity will always converge to a real point behind the lens. Okay? Whereas, let's take the case of biconcave lens, and let's understand why this will always have a virtual focal point. Okay. So let's work out an example. This time let's take this surface as having radius, let's say 60 centimeters. This surface as having radius, let's take something different this time. So let's take, this one is appearing larger, so let's take 120 centimeters. And refractive index of glass again and the thickness is focal length. In fact, now what we'll do is we'll find the focal length firstly, and second, find the position of the image for the point object which is shown below in the diagram. So, this I am keeping at a distance of, let us say, 90 centimeters from the common pole. So for this, what will be the position of the image? So to find the position of the image, you'll have to go back to the formula we developed before the lens maker's formula. Before we found out focal length, we saw that 1 by V minus 1 by U was that formula. Okay. And then in lens maker's formula, the right hand side actually became the focal length. So this becomes 1 by V minus 1 by U is equal to 1 by F. So this is the lens formula. Just a small variation from the mirror formula. Instead of plus, here you have minus. So this is called the lens formula or the UV formula for the lens. We remember U, V and F are with sign. They have to be substituted with sign. So you can make use of that in the second part. Okay. So just work this out quickly. Okay, so people just going through your answers. Focal length, okay. Yeah, so this time you will see it will work out to be a diverging lens of focal length something, 80 centimeters I think or whatever. So for example, if I take the situation that light is incident from here, I take this as the negative side and take this as the positive side. So the first surface's center of curvature is here, and the second surface's center of curvature is here. This is my, so in this generic case, this will be my surface 1, which has PC1 equal to 60 centimeters. And this will be my second surface, where PC2 will be 120 centimeters, I think we have taken. Yeah, okay. So I will take, with the proper sign convention, I will take R1 as minus 60 and R2 as plus 120, okay, in centimeters. And hence, with the proper sign convention, 1 upon focal length will become mu minus 1, so that is 3 by 2 minus 1 into 1 by R1, that's this, minus 1 by R2, that's this. Okay. That formula. It's always, it's this generic formula. So your focal length is such that you can take minus half outside and you have 122 plus 1 plus 3. So as you can see, your focal length will become minus 80 centimeters. So minus 80 shows you that means that the image is formed on the same side. It's a virtual image. So that shows you that these rays, after refraction, they will emerge out like this. These parallel rays after refraction, they will emerge out like this, such that when you produce them back, they give you an image somewhere here. This image is the position of the focal. So that PF, which is the magnitude of the focal length here, which will become 80 centimeters. But with our sign convention, it will be written as minus 80. Similarly, if a light had come from the opposite side, you would have got the focal length as positive. Light had come like this, you would have come to this conclusion, that light is emerging out such that the focal position is here. Okay. Now for the second part, we are keeping the object at a distance of 90 centimeters. So we'll just use the UV formula. So we know that if this side is negative and this side is positive, and the object is on this side, okay, then where is my focal position? My focal position would be here, wherever, somewhere here. So we had got the focal length as how much? It was 80. So somewhere. Okay. So that is why in this case we'll have to take the focal length as minus 80 centimeters. But this is where you have to be careful about how you apply sign convention. Just because it's a diverging lens, don't take it as minus 80 in every case. It really depends on which is the virtual side and which is the real side. U will take as minus 90 centimeters and V we can find out. So 1 by V minus 1 by U is equal to 1 by F. This is the formula we use. So we'll see that 1 by V minus 1 upon minus 90 will become 1 upon minus 80. So we'll see 1 by V becomes negative of 1 by 80 plus 1 by 90. Because here is with a plus sign, so bring it that side, comes with a minus sign. Okay, so this we can write as minus of 9 plus 8 upon 720. So the V actually becomes minus of 720 by 17, which will be approximately, let's work it out and tell you. So from the ray diagram also you'll understand why this happens. Okay, just explaining for a moment. Kitna tha? 720 by 17. So it's about 42.4 centimeters approximately. Now you'll understand why this is happening by just a generic case of understanding what is happening to the rays. This ray over here, it will tend to go in which direction? Towards the normal. So it will go a bit like this. But then again, it will tend to bend away from the normal. So that is why when you're producing it back, well, this is a very exaggerated diagram, but when you're producing it back, this gives you an image somewhere over here. It's always divergent. So whatever rays which come here, they always tend to diverge more. That's the idea. They always tend to diverge more. So always get this kind of an image. So you can see that you are getting a virtual image. Minus. This is virtual image. 42.4 centimeters in front. So what it also means that it's a virtual image means that if you're viewing from the other side, this object will appear to be here. So this virtual image concept also means here that if this was the object and this is where the image is, an observer like this will actually be able to view this. So this observer actually sees the object to be at the virtual point I. But if you put a photographic plate over here, you will not receive any image. Whereas in the case of convergent lens, is the other way around. An observer on that side will not be able to see any image. But if you put a photographic plate over there, you will be able to receive the image on it. You'll be able to take a image. I mean, you will be able to take a what can you say, like a replica of the image. So that is the concept over here. So very good, people. So you have got all this correct. Okay. So this is where we'll conclude today's lecture. I'll be sharing the whiteboard notes, and also now with today's lecture, actually now what is remaining in lenses is just a few tricks like combination of lenses and then silvering of lens, a direct formula and all that. But the point is you can always solve those questions even without using tricks, because now you know the lens formula, you know the mirror formula in general. So you know how to solve everything by fundamental application of one event after the other, one event after the other like that. Okay. So next lecture will basically be a problem solving lecture, where we'll see a few tricks of how to use combination of lenses or lens with mirror, etc. Bringing a mirror in contact with the lens or keeping it at a certain distance, but using the combination, those kind of things. And we will also be doing a detailed analysis of the concave and convex lens in terms of, like we've done for the mirrors. So where you keep the object correspondingly where the image should be produced, what kind of object gives real image, what kind of object gives virtual image, things like that. And we'll also be discussing the role played by virtual objects in quite a bit of detail, again for lenses. So that will be the only theory part next time. Otherwise, the next lecture will be purely various types of problem solving of combination of lens and mirrors. And then one more final lecture after that, we'll be discussing about prisms, which is slightly different to our discussion till date, especially thin prisms. And in that lecture, we'll also be seeing what is called the defects of lenses and prisms. Defect in the sense that defects happen because of two reasons. One happens because of what is called spherical aberration. That to a certain extent you already understood. Whether you take spherical mirrors or spherical lenses, etc., there is aberration that occurs because along with your paraxial rays, you also have non-paraxial rays. And the non-paraxial rays don't actually give you sharp images. So the actual image that you get is always a bit blurred. in these situations compared to the kind of image you get for a perfect plane mirror or something like that. So that is called spherical aberration. But more importantly, there's also something called this thing, aberration due to chromatic aberration. But the chromatic is to do with color, and that happens only in the case of refraction. So it happens only in the case of prisms and lenses, not so much in the case of mirrors, because the phenomena of refraction also results in dispersion of light into its component colors, because the refractive index, we will see later, is ultimately dependent on wavelength or dependent on color. So that results in, if you have white light coming from infinity, or you have a point source of light which is creating a combination of wavelengths, then the image will look slightly split in color, and there will be some blurriness in the image where the blurriness also corresponds to the color getting split. So that is called the chromatic aberration. Okay, so we will discuss about that. Yeah, now coming to a syllabus about the minor test. Your syllabus for the minor test will be up to this point actually. It will be up to lenses. So your prism will not be there in the syllabus, and nor will be aberrations. So your syllabus is everything excluding prism and excluding this thing, aberration, chromatic and spherical aberration, and also excluding microscope and telescope, that is optical instruments. Okay? So it's up to this point, up to thin lenses analysis. Okay? I will also send you on your groups. Yes, about the assignment also, I'll give you a group of questions from the module which you can do. And now you can complete HCV fully, because HCV's chapter on geometrical optics is up to this only. The next chapter deals with dispersion, and that's where prism and all that comes in. So you can do that. I'll also send you a list of questions from the this thing PDF module that you have, and that should be more than sufficient. If you want to do more questions, I can always recommend some questions from either DC Pandey optics or from Cengage also. Okay. So that's it for today, people. Hope you understood this lecture fully. Okay. Again, quite a crucial lecture in this series for us today. Okay. So if you have any other doubts and things, you can keep WhatsApping me and sending me. I'll help you out with that. Okay. So all the best, and prepare well for the upcoming test. You have quite a bit of portion in electrostatics and things also. So you can keep discussing any doubts you have with me, especially geometrical optics, but even other subjects, it doesn't matter. You can discuss. Okay. All the best. That's it, people.